It's a calm morning. The engineers who built this bridge, they're not worried. I mean, why would they be? They ran the calculations, they checked the numbers, they built it to survive winds 3 times stronger than what's blowing today, 64 kilometers per hour. Just a moderate November wind. You know, the kind that might make the tea in your cup tremble a little, but nothing more. And then?
The bridge starts to move, but not just swaying randomly, against the wind. Something is different.
It's moving in rhythm. One side goes up as the other goes down, and then it reverses, rising, falling, rising, falling. A slow, almost hypnotic, and terrible oscillation, like the bridge has found a pulse that it likes, and it's just decided to see where it goes. This goes on for hours, and then, at 11 in the morning, the third longest suspension bridge in the world just falls into the river. And the wind? It's still blowing at that same 64 kilometers per hour. Now just stay with that image for a second. Hold it in your mind. Because 60 years later, in a totally different country, on a different bridge, over a different river, the same thing is about to happen all over again. And this time, the reason why is, well, it's even more unsettling. So let's jump to London, the Millennium Bridge over the Thames. It's June 10th, 2000. It was built to celebrate the new century, and on its very first day, 90,000 people cross it. And somewhere in that massive river of human beings, somewhere between one person's footstep and the next, the bridge begins to sway. Sideways, really gently. You could barely even feel it at first.
People feel it, and they kind of look down at their feet. A few grab the railing. But most people, they just adjust how they're walking, the same way you would if the ground beneath you shifted a little. They plant their feet a bit more carefully. They start to time their steps to the movement of the bridge. They have absolutely no idea what they are doing. They have no idea that by adjusting their steps, by trying to keep their balance, they are making everything so much worse. The bridge had to be closed just 2 days after it opened, and it stayed closed for 2 years. So you've got 2 bridges, 60 years apart. One was brought down by the wind, the other was brought to its knees by people who were just trying to walk carefully. It was the same physics, the same formula, the same warning that nobody read in time.
From byte to terabyte, where one small idea grows into a universe.
So to understand what destroyed 2 massive bridges, we actually need to start with something much, much smaller. A swing. A Joula. You've pushed someone on a swing. So, believe it or not, you already know something about resonance. You've known it since you were a kid. You just didn't have a word for it yet. So, here's a question for you. Let's say you want to push a kid on the swing as high as they can possibly go. You've got 2 ways to do it. Approach 1. Just push as hard as you can whenever you feel like it. No rhythm. Approach 2. You push gently, but your timing is perfect. At the exact same moment every single time. A small force, but perfect timing. Which one gets the kid higher? Come on, you already know the answer. You've always known. It's the second one. Always. And it's not because the pushes are stronger. In fact, they're weaker. It's because they're timed. It's because each little push arrives at the exact moment the swing is ready to receive it. And each gentle push adds to the one before it. The energy just accumulates. This is resonance. It's when an external force shows up with the exact same rhythm a system already wants to move at, what we call its natural frequency, and the energy just builds up, cycle by cycle. The size of the force, it's almost irrelevant. What matters, the only thing that matters, is the timing. Think about a classical singer shattering a wine glass with her voice. There's no contact, no force. It's just sound. First, she'll hum softly, and she's feeling for that faint vibration, the frequency at which the glass itself wants to sing. And then she finds it. She steps back, she opens her throat, and she sings that one note. Pure, unwavering, and sustained. If you watch this on a high-speed camera, you can see the rim of the glass oscillating, deforming, flexing with every single sound wave. And it grows, just a tiny bit with each wave. And then, it shatters. Not because of force, but because, at the right frequency, sustained, patient, perfectly timed, sound can destroy glass completely. Resonance doesn't need strength, it just needs rhythm. Okay, now let's scale it up. We're going from a wine glass to 60 men. Let's go to Manchester, England in the year 1831. You've got 60 soldiers marching across the Broughton Suspension Bridge. Left, right, a perfect synchronized rhythm. And the bridge, it begins to shake.
And I mean violently, unexpectedly. The bridge started oscillating so severely that the chains holding the deck just snapped.
The whole structure partially collapsed. Now look, a bridge does not collapse under 60 people just walking, but 60 soldiers walking in perfect military step, with their footfalls synchronized, rhythmic, arriving at a frequency that just so happened to match the Broughton Bridge's own natural frequency. Well, those 60 soldiers weren't just a load on the bridge. They were like a tuning fork being pressed against it, and the bridge resonated until it broke.
This incident went all the way to the top of the British military command, and the response was a simple, permanent order that's still in effect in every army in the world today: break step. When soldiers approach a bridge, they stop marching in unison. It's not because 60 soldiers are too heavy, it's because 60 soldiers marching in step are a resident driving force. That order has been in the British Army drill manual for almost 200 years. So, a singer shatters glass, 60 soldiers collapse a bridge, and still, a century later, nobody checked the numbers. So now we go to the formula, because the formula had the answer all along.
The intuition is ancient. The soldiers knew it. The singer knew it. You knew it on the swing. But the warning was always there. It was written in the language of the universe.
T equals 2 pi times the square root of m over k. I know you've seen this before. It's right there in Chapter 10 of your Class 11 physics textbook. Simple harmonic motion. You've substituted numbers into this equation, you've solved numericals with it, but here's what this equation is really telling you. It's not telling you how to calculate a number, it's telling you the rhythm of an object.
And you've heard this your whole life, just in a different form. Think of a tanpour. You know that instrument that holds a single sustained drone? The singer finds that same note, locks onto it, and the sound becomes larger than either of them could make alone. That is resonance. The tanpour string has a natural frequency. The singer's voice matches it. The energy accumulates. You see, the universe doesn't distinguish between a tanpour string and a suspension bridge. They all have a natural frequency, and the formula is identical.
So let's go back to our two bridges. For the Tacoma Narrows, the wind itself created a rhythm, a kind of pulse that perfectly matched the bridge's own natural desire to twist. Each pulse fed the next. The oscillations just grew, relentlessly, until the cables failed. It wasn't the force of the wind that broke the bridge, it was its rhythm.
And now, London. The Millennium Bridge's natural side-to-side frequency was approximately 1 oscillation per second, and the side-to-side force produced by a human footstep also about 1 force per second, 1 hertz. It was an exact match.
So, here's the crucial point. When the bridge started to sway, people instinctively adjusted their walk. They synchronized, hundreds, then thousands of them, all stepping at 1 beat per second. The people, they were the rhythm that broke the bridge. And that rhythm was always there in the formula. This is the difference between a formula you have memorized and a formula you have understood. A formula you've memorized tells you what T is. A formula you've understood tells you what will happen to a bridge before you even build it.
What I want you to take away from this isn't just the story of a disaster. It's something quieter. It's this: the universe is mathematical. And what that means, what it has always meant, is that the physical world is readable.
After Tacoma Narrows, engineers started computing the aerodynamic behavior of bridges. Today, every major suspension bridge is tested in a wind tunnel. After the Millennium Bridge, every footbridge design has to include a lateral frequency analysis. 2 disasters, 2 permanent changes to how humanity builds. Both of them were preventable by the formula that was already known, and both were corrected by finally understanding what the formula really meant.
The next time you open your textbook, look at the equations differently. Don't just ask yourself, how do I solve this? Ask, what is this telling me? What rhythm is this describing? What would happen if the world just happened to match that rhythm? That question is the difference between a student who passes an exam and a student who understands the universe. One is a useful skill, the other is a way of seeing. Bridges fall when the formula is memorized but not understood. Understand the idea, not just the formula, because the idea is what saves bridges. The formula is just how we write it down. This is Byte to TeraByte, one concept at a time.